It's not easy for us busy geotechnical engineers to keep up with industry trends while keeping up with our engineering work. Therefore, it's our goal at the Geotechnical Engineering Podcast to help you do just that. We strive to keep our listeners informed on important industry topics and also to help educate you on interesting technical topics and trends in the geotechnical world. In this episode of the Geotechnical Engineering Podcast, I'll be talking about Brian Dorwart, PE, PG, a senior consultant at Brierley Associates. Mr. Dorwart is a registered professional engineer in 25 states and a registered professional geologist in 2 states. He has over 40 years of experience in underground engineering and more than 30 years of design and field experience with various types of trenchless engineering, including horizontal directional drilling, or HDD, small diameter tunnels, and underground utility rehabilitation. And in this episode, we'll be talking about trenchless technology, and we'll also review the current status of trenchless technology with a concentration on horizontal directional drilling. I'm your host, Jared Green, and I'm excited to be bringing you yet another episode of the Geotechnical Engineering Podcast. And with that, let's jump right into today's episode.
This video is also brought to you by Menard USA. Menard USA is a specialty ground improvement contractor that works nationally, providing design-build ground improvement solutions at sites with problematic soils. Menard works closely with civil, structural, and geotechnical engineers to minimize foundation costs for wide ranges of soil conditions, structure types, and loading conditions. To learn more about Menard USA or for help on your next project, please visit www.menardusa.com.
Brian, welcome to the show. It's great to have you here with us. I've been really looking forward to this conversation. So how are you doing? How are you feeling?
Doing well today. Sun is out, weather's good.
Excellent, excellent. What more can we ask for, right?
Yeah, nothing more than no snow and no blizzard.
Yeah, exactly. Oh my goodness. So can you tell our listeners a little bit more about yourself and what is it that you do on a daily basis?
I'm obviously a geotechnical engineer, which doesn't mean a lot to a lot of people. It means mostly that we work with dirt. To put it in a common term, we work with dirt underground. And a lot of what we try to do is figure out what the dirt's going to do when you dig a hole in it. Is it going to stand up or is it going to collapse? And so we try to actually predict that. Understanding Mother Nature is really not a friendly all the time to you. So we try to predict as best we can based on very limited data. And for different types of underground projects, come up with an idea. How can you build it and how will it stay up? Not like the Leaning Tower of Pizza, which didn't stay up. Well, it's partially up anyhow. But, how do you keep it in one spot? That's what a geotechnical engineer does. In my background, I started out actually as a driller. After I got out of school in geology, there wasn't a lot going on out there except for going to Iraq and Iran for logging for Schlumberger. And so instead I took up a job with Rochester Drilling Company. So I worked as a driller for quite a few years, and therefore I'm got a lot of exposure to different geotechnical engineers logging the test borings. Getting tired of being called a dumb driller all the time, I went back to school. Got a master's in civil engineering, geotech specialty. So now I'm the dumb engineer and the dumb driller. So can't help you much on there, but it's turned out to be a very exciting career. So it's something I take passionately and I like what I do.
Great. That's great. It's, as a geotechnical consultant, I can only imagine having that background as a driller and also as a geologist, and then having that background with the geotechnical engineering, as a master's, you bring a lot to the table when you're trying to solve problems. So that's pretty cool. Hopefully the solutions are practical, right? And buildable. So that's always what the desire is, right?
That's what takes a lot of time. I found time and experience. You just learn in school, you're just scratching the surface.
Mm-hmm.
After that, it's applying what you've learned, because you probably know when you get out of school, more computer work, education, equation, all this stuff, more probably than anyone else out there.
Yeah.
Because you're well trained at university. What they have a problem providing is that hands-on exposure.
Mm-hmm.
What really does it mean to go out and write a report, recognizing that what you're saying and what you're doing is going to be followed because you're now a professional, and your responsibility is, this is what civil engineering is to the public. If you screw up, people die. So it's a heck of a responsibility, and that's where the hands-on experience comes, and that's a lot what I've relied on pretty much all my life. Is various firms have provided senior people to help me through and guide me through the projects, and so that's been helpful. And I'm trying to return that, so to speak, with discussions like this and lectures at universities and papers and stuff, because it's something every professional needs to provide the feedback into their own industry to maintain it.
No, it's great, and that's what it keeps things rich. And the reality is that you hit the nail on the head, and that with geotechnical engineering, we have to make these very important decisions based on very little information. I mean, we think about it; it's very little bit of information.
Well, exactly.
Right?
There's, one of the examples I have is we're going underneath a river with a directional drill, and we'll learn about that in a second.
Mhm.
But I have a underground excavation. I have to go underneath the river, and I'm in the Northeast. And the rivers go wandering all over the place, but in the Northeast and in the Northwest, anything that's in a glacial or sometimes other type of environments, the streams as well as the land features, topographic features, are controlled by the structure of the rock underneath it.
Hmm.
Well, to be able to have a crack where a river's running in rock, it's usually a fault zone or a real weak zone like a pegmatite.
Okay.
So if you do test borings on either side and find out what the parent rock is, have you really answered the question of what you're going to encounter? If that's the monster under the ground that you just missed.
Yeah. Oh, you're absolutely right. I mean, the reality is that you know exactly what it is when you're going through it, but we need to know
Yep.
well before that when we're putting together contract documents and the like, right?
Exactly. You have to understand the best degree, but recognize that you can only do with what you're given with regard to budget and access. So you're not going to know everything, and you have to go into the construction with the knowledge that you don't know everything. We don't know really very much. And so as you're watching the construction develop, it's telling you what the ground is letting you do. Learn from that and talk with the contractor, be flexible, adjust. Your design is a prediction. It's only as good as the data you had, and the next set of data is construction, where you are seeing everything. And given that we're perfect, you can follow design. Good luck.
Luck, it's right. Perfect in geotech. That just sounds funny. It's hard to say that with a straight face, right?
I know, it's like Dirty Harry saying, "Do you feel lucky?"
Wow. So let's talk a little bit about trenchless technology. What is that? Like, what is that?
It's a good question, because up to maybe 20 years ago, never even had a word like trenchless technology. It's one of those new ones in the dictionary. But trenchless technology doesn't mean I do all my work underground, but the great majority of a project will be done underground without disturbance at the ground surface, with the exception of you got to get into the ground and get back out. So you'll have an access at either end. So trenchless has a pretty broad meaning, because what can you do underground? Most of it requires some sort of remote underground, so you're not putting lives and limbs at danger. That gets into, we have a huge amount of infrastructure out there already. It's all underground. Can I rehabilitate that infrastructure underground without having to dig the street up? And can I make that last a long time? There's an entire rehabilitation part of trenchless technology out of there. Another one is, can I make reuse of abandoned utilities? Say, break it in place and put in something inside it that'll work for the new product. Somehow reuse that already existing corridor, so I don't use up valuable quarter space. You'll find in many cities, if you actually open up the ground in downtown, like we did this in High Street down in Boston. We literally, without taking a big step, walked across on the utilities in the street. We could not find enough room even to get like a 24-inch shaft down to a tunnel below. Didn't exist.
Wow.
So, and when I go down on the ladder, I'm sort of on the round side. I don't fit in a lot of spaces in between the utilities. That's a problem. So there's the replacement and recycling of quarters is another part of the industry. And then there's the new construction where we need new infrastructure, and the utilities in the urban areas and other areas can either do restrict you quite a bit from where can I actually get, like maybe you have to go very deep to have a clear utility path, or maybe you're in a city and they don't want you to dig up the highway or this street. Maybe you're going under sensitive wetlands and nobody wants you to dig that up unless you absolutely have to, but it's not preferred these days. The wetlands are too valuable and it takes too many years. They will recover, but that's over time. So have you done any good? You can do better. That's what the trenchless technology is, using tools that can handle underground, for lack of another word, tunnels or anything. Can we rehab them? Can we replace and use the same corridor? Can we create something new? And there's a whole bunch of different equipment and technologies now that are just exploding as an availability to make this happen. It's gained a lot of popularity, not to mention that a lot of the trenchless techniques, actually their carbon footprint is only 5 or 10% of what an open excavation carbon footprint being, to do this construction, how much carbon are you releasing in the air through all your fuels and everything else you're doing to create the project. With trenchless technology, it's only 5 or 10% with an open cut, which means you go in there from the surface, you rip it all out, put in whatever you want and bury it and put a new street on. So environmentally, it's actually a very desirable, and politically, it's a very desirable technique. So much so that our southern border, Texas, all the way up to California, is riddled with underground pipelines and corridors. A lot of them use things like vacuum tube, sort of like a vacuum cleaner, to suck drugs across the border without people knowing it. So it's pretty effective. We go around now listening on the ground along the border for where these things exist. We can find them. So beware if you're trying to smuggle with trenchless technology. They will find you.
Wow, there's a lot going on underground. A lot going on underground. What would you say? What or who would you say drives innovation and progress in something like trenchless technology?
That's a really good question. I actually just did an article for a magazine on that. And some of the research and some of the other research I ran across, I'm certainly not innovative in this approach. There's a lot of people interested in history. It actually goes back, way down to the Roman times. Look at Roman aqueducts. How many of them are on the bridges, which we can see, but how much percentage is in tunnels underground? Right? That's trenchless technology, is a tunnel. Of course, back then it wasn't remote because you had to put people in there to chip it out. But what it was is the public had a need because of urbanization. How are you going to solve the need? The engineers back at the time and the owners, et cetera, and the contractors said, well, we got to dig a tunnel because it's too much to dig off the top. So that is pretty much followed the industry all along. There's opportunities due to how civilization has developed over the years and moved around in urbanization or in dense clusters, that's prohibited access from the ground surface for a lot of reasons. It's cheaper to go underground, even if it's a higher cost, than it is to tear these markets apart. Like, nobody wants to tear down a brand new building so you can run a pipe underneath it. So you create that as an opportunity by just the urbanization. Then you have people always want to make a buck on it. That's your contractor. And the contractors, people think they're gambling when they go to Vegas. Contractor is your biggest gambler in the world. They gamble all their assets every day they make a bid. They've got to build it. And to do that, they got to come up with ideas, which means you got to have tools. And so a lot of the contractors come from a varied background. They work with manufacturers of different tools. So we've been finding over the years right up, through England and their tunnels there, through underground water lines, everything else. Today, it's even the same on innovation. Create the opportunity with the owner, and then let the contractor and the manufacturer of the tooling come up with a way to solve the problem. It may be something they're familiar with and they do it every day, or it may be an interesting one where we got to come up with, say, for instance, there's a product called pipe ramming out there, a technique called pipe ramming. That's basically has the concept of if you can't drive the nail because it's a railroad spike going into a 2x4, get a bigger hammer. Don't drill a hole, get a bigger hammer. And that's what they do. They take big hammers used for pile driving. They wanted to go sideways in the ground. Why not make the pile driving hammer go sideways? So they built these pneumatic hammers that came out of the drilling industry, turned it sideways, and now they're shoving pipes in the ground for utilities with a bigger hammer. And these hammers, they can now install concrete box culverts 14 by 14 feet square under railroads for pedestrian access, et cetera. 30 years ago, 40 years ago, never even heard of it. So that's an example of an innovation in the industry of you have an opportunity. Somebody had knowledge of pile driving. The tooling manufacturers figured out how to make the tool go sideways. And then the idea is you just got to make the hammer harder or bigger. And these hammers weigh, 6, 8, 10,000 pounds. So they learned how to make them bigger. And of course, with all engineers and contractors, bigger is always better because it's more power. And that's what really gets us excited in the industry. Big horsepower.
There you go. That's really cool. I love the fact that, and I'm sure the listeners will appreciate this, that you have a challenge and that challenge becomes an opportunity, right? And from that opportunity, if people are all working together and attacking the problem or a challenge from different perspectives, you come up with a solution that's good for everybody. So that's really cool. And, in simplest terms, instead of going vertical, let's go horizontally, figure it out, right? And it works.
It's a detail. And yeah, there's problems associated with it. Mm-hmm. So what? That's your job as the engineer to do the little bit where you can help. The contractor brings to the table what they can help with. The manufacturers bring to the table what they can help with, but it all comes from an opportunity. Definitely, and there's, of course, lots of shows on opportunity of the invention of clocks and other simple things that people have seen on TV for years. The history of manufacturing is, full of examples.
You're absolutely right. What would you say, as far as construction techniques that compose the field of trenchless technology? There's a litany of them, but can you talk through some of those for us?
Oh, we have, again, for simple, starting back at the pipeline rehabilitation, they came up with in the 70s something called the CIPP, cast in place plastic. It's not really cast in place pipelines, but I call it plastic because that's what they make it out of. That's a process where you take a resin saturated tube and water and you just shove it while the resin's still unset into a pipe, and then you expand it with water, air, something to make it expand out, touch the side of the pipe, then you cure it in place. You just manufactured a new pipe using the host pipe as a form. So you now just completely rehabilitated or replaced a pipe. That's one of the tools. So it requires the knowledge and technology to come up with the resins and the tooling to simply take water pressure and invert a tube so it comes out round in the host pipe. Other ones in the, like in the replacement, or the replacement and the things. That's what I just mentioned, like in the pneumatic hammers, where you can take and hammer a new pipe in. You can also do what's called bursting, where you take the exact same hammer. So now a contractor has one tool that can do two different jobs. One of them being they can shove a new pipe in the ground. The second one is they can put a tool on the front, and just like getting a bigger hammer, the tool in the front acts like a can opener, and it'll split open an existing pipe and let you put in the same size or a bigger pipe in the same quarter very fast. For instance, 300 feet of new pipe, you can put in about 2 hours. Of course, it takes you a lot of time to prep it, but the actual construction, no disturbance on the surface, providing you do it right. And you're putting in a new pipe along the same quarter. In the new pipe, you have things like what it used to be a hand excavated tunnel. There's a lot of labor in that and a lot of danger in it. All right. How about if we can do that remotely? So we put in a machine that can cut the soil, cut the rock, whatever it is, remotely. So you're sitting at one end of the tunnel. These are called either tunnel boring machines, or when you're into the trenchless small stuff, they're called micro tunneling. And some of those, like the auger boring machine, one of the first ones ever developed, those started back in the 1800s with a need, a number of needs in there, but the more colorful one is the auger bores used in Pennsylvania and West Virginia back in the 30s, where they wanted to mine coal, but the roof kept collapsing. Well, if you take an auger boring machine, which was developed specifically for this problem, you can drill sideways in a coal seam and extract it all without ever going underground. That was a huge market opportunity for contractors that had these types of machines to go into the coal mining industry and help them out. Other newer techniques are like directional drilling, horizontal directional drilling, where I can sit on the ground surface, launch your regular, what it used to be is a drill rig for explorations, which started as a water well tool. All right. So now you have a water well tool. Well, I want to now steer it. Well, when they had water wells, they used to be able to steer it by throwing a chunk of wood down there on one side and deflecting the bit. Or if you have a deep enough hole, the drill string's always, it's not going to go straight. It's going to go down and to the right, make a corkscrew, and eventually you can't go any deeper. So you run yourself out of problems. But can we take advantage of what's happening in the drill string due to defects in tooling, which is how we developed, and I take no credit for it. This is Martin Sherrington's development out of California. He found out when he took different types of worn out bits, just like a crowbar, when he hit a rock, the rock would deflect it. We made a tapered bit on the front. When he shoved it in the ground, it actually started turning. In the different shapes he put on the bit, he could actually somewhat steer it, which means at the end of 1,000 foot, if he came up within a couple 100 feet, he was doing really good. He had no way to find out where he was, but he could steer. Then he added the oil field technology of how do you steer it and where are you? Brought in oil field technology, which started out as like it's a whipstock is what they call it. Is you take a picture underground and it gives you an XYZ where you're at. It takes you about 2 hours to find out where you are. Well, that's not commercially very good. So he came up with better ideas. How do you steer it and get it timely? Yeah. So that's what directional drilling is. Now I can put a bit with a tracking package in the ground, and I can hit, I'll say I can hit a stake. I can always hit a stake at the other end. It's just how much you want to pay to hit that stake. If you want to be economical, I'll come up within 50 feet of that stake after maybe, 2 or 3 miles of drilling. So I can put in infrastructure, and I've done this, 12, 14,000 feet long with, I can hit a, spot on the ground at the end of that other end of where I'm drilling to. And I can do that up to, well, I just finished a project down in the city of Miami Beach, South Beach, right downtown, where we drilled in a 3,000, the short one, 3,000 feet, and we installed a 54-inch plastic pipe. It's the biggest it's ever done. It's the longest it's ever been done for that size pipe, all done with trenchless technology. And the mayor allowing us to go under streets, hoping we wouldn't break anything, which we didn't do. So that was a good thing. There's been a bunch of articles and stuff on that project, but that was very interesting. How do you set up downtown in an urban area? Don't shut any businesses off. All businesses have to have full access. And we found 2 spots underneath one street. The only thing we had to do is our pipes were on top of the street, because you drill all the way through, you grab the pipe at the far end, and you drag it back into your hole after you make the hole big enough. Well, where are you going to put all that pipe? We put it down the middle of one of those suburban streets. They had a greenway, or it was 4 lanes wide. We took the middle 2 lanes to put this 54-inch pipe, assemble it for 3,000 feet. We couldn't get that, so we had to splice it together during construction, but we still had several blocks. You couldn't cross over the blocks. We had to build stairways to go up on top, get over the pipe, and go back down so they could get to the beach. And that was a big deal. We also had to, unfortunately, put a noise barrier, is what we called it, around the drill rig, because we were literally 1 street over from South Beach. And that was our noise barrier. What it was really for, you got to keep the driller's mind on the job. And that's hard to do. So we put them in a box.
Okay. Whatever it takes, right?
Whatever it takes, get your job done.
That's awesome. Well, that sounds like a really cool project. As far as trenchless techniques, I mean, what's the one that you enjoy the most, and why? I know it's hard to pick a favorite, but which one do you enjoy the most?
Well, I adventure into all of them pretty frequently, but my favorite is still directional drilling.
Okay.
Starting from a drilling background, and now getting drills out there with 2 million pounds of thrust and pull. That sounds like a lot, but when you think about, I maybe need 4 to 5 million pounds of thrust to break rock, it's still a small number, but it's a huge amount of horsepower, several 12-cylinder diesel engines to run, a couple of the pumps. Big power, steerable. You can shove the end of the drill anywhere you want to go through foundations, just plain horsepower, and the ability to be precise with it. That's always sort of been my passion, is I like to use horsepower, but I like to use it in a right position. Don't know where that came from. Sorry about that.
No worries. Let's see. What are the components of horizontal directional drilling, or HDD projects? Like, what are some of the components?
Oh, you obviously have a drill. Drill it can go anywhere from fitting in the back of a pickup truck for, say, I want to go 200 feet and go into someone's house from a sidewalk. I can set up on the sidewalk and run a sewer connection, water, whatever, just with one rig. And you don't need anything else. You need that and your drill rods and a bit, and then a place to go. And then as you get bigger, you get a little bit more friction. You add water and what's called bentonite clay to it to make it slippier, which allows you to go a little bit further. That takes another piece of equipment, a big tank and a shear mixer, which is just nothing more than a high-speed, like what you use for a milkshake, making a milkshake. You make a milkshake with your bentonite clay, you shove it in the ground, lubricate your rods and your drill bit. And you also have now a steering package on it called a walkover, which is nothing more than a radio beacon. And you walk along the surface and find where it is in the ground. And that tells you where it is. And then based on that, your driller's supposed to be able to put it where it's supposed to go if he knows where you are. Sometimes he's lucky, sometimes not, but that's the next tool. Then as you get bigger and bigger, you got to make the holes larger. So you still drill the pilot, you still steer it with some electronics in there, which get very sensitive. I can go down 2,000 to 3,000 feet with these electronics and know where I'm at. I probably got to know it within 1% of where it is. Actually, I know exactly where it is within about an inch. You just, the tolerance on that, you know where you are within an inch, but if you go looking for it, you're going to tell people it's within, say, plus or minus 50 feet is really what you know, because it's so deep. And that's where we get into assessing precision versus accuracy. One of them is where are you actually, and the other one is how precise you can be. So you can be very precise, but don't have a clue. That's directional drilling. So then you get bigger and bigger with bigger rigs. Bigger rigs come in, say a 1.5 million pound rig will come in on 23, 24 tractor trailer loads. Your drill might weigh 115,000 pounds, and then you'll have 2 or 3 other tractor trailers of pumps to pump your drill fluid down the hole. Then, because there's so much fluid, millions of gallons, I'm pumping this down the hole at 700-800, upwards of 1,500 gallons a minute. I got to clean it, because otherwise I'll go broke on all the drill fluid. So it comes up out of the hole. We have what's called a cleaning equipment, which is just a bunch of screens that take all the junk that came up out of the hole, all the cuttings, and take them out of the drill fluid and let us recycle it down the hole. And so that's the biggest piece of equipment, with all the amenities, and all of that is designed to match each other. There's, in any underground construction, you only have one access point. So your drill bit, your drill heading, everything is only working in one spot at a time. So you got a $60,000, $80,000 a day of equipment on the ground surface. All of that is what it takes to put my pilot, my 12-inch hole, in the ground. So if something happens, I got a big problem. So you got to tie and match all the equipment, so whatever speed you can excavate at, you can recover the cuttings at the same rate and get them out of the hole that you're moving forward. That's where the skill comes in, is mixing and matching with the ground. So knowing how fast you can cut it, you've got to get the cuttings out of there as fast or faster than you can cut it, and keep things clean. So you can see each one of them starts out very simple, but expands. There are a lot of little modules you can add on to it to do the bigger and bigger projects.
All right. Thank you so much for that. It really helps to see just, what happens as you start to scale up. And you touched on one of the common problems, but what are some of the sources of common problems in the industry for horizontal directional drilling?
That's, again, a real good question. Now, I'm talking now from being in the field for many years, and also for many years doing forensic studies on drills that didn't work, including court appearances, et cetera. Change conditions is your common one. Well, how do these occur? We find a lot of them is, and is sort of the underlying common thing, is inability of having a common expectation between the owner, the engineer, and the contractor for what does it take to physically construct this package, and what is that going to translate into for cost. That has to be realistic. Any one of those components will kill a job if it's not paid attention to. The second most common one is being given a project in underground with no data, which is probably 40-50% of the jobs for directional drilling comes in with no data. We're supposed to guess at it, and they say, when we go in and present this as a change condition, well, everybody knows about that. I'm not anybody. I'm a contractor. You've given me no information. How do you expect me to tool up for it? Because I can handle any ground with a directional drill. I have enough horsepower and tooling. I can handle any ground. But one setup on the tooling will only handle a narrow range of subsurface conditions. If all of a sudden you have different conditions, you got to pull out, retool it, and go back in. Now you can do it, but that's cost you probably a week. And recognize on a bigger job, $60,000 to $100,000 a day. That's a lot of money of sitting around doing nothing, because you can't do anything until you get that one whirligig jig in the front to go to the right. So, and make a hole. So you got to make a hole. If you're not making a hole, you're not making money. So that's the second thing, is lack of data, or inappropriate, or um, not enough data for the problems and the risk at hand. If you say out in some of the plains, and everyone thinks the plains are all flat, they're not. But where you have horizontal ground, you might be able to get away with a couple of borings. If you're in New England or in a volcanic area or anything like normal, people encounter all the time, the geology is very different. And you got to have tooling that'll encounter all of it or fix it, and you got to price it that way. The big reason for that is you can have almost a 1,500 times difference in a production rate if you have really good quality ground versus you have a real hard rock ground. Imagine what that does to the cost of the project. And a contractor has to bid it somehow, and he has to be able to allowed to bid it with some way of getting the project realistically. So you can't be ultra conservative, and he's still got to be able to cover his cost on getting the project done. So you need enough information and recognition that as an engineer, you got to say, you guessed right or you guessed wrong, and go back and adjust it and make it right for the contractor and for the owner. And this is one of the most difficult things I've seen, is the difficulty of engineers to create a realistic expectation in the owner's mind of what can go wrong and who's carrying the money and who's carrying the responsibility for it. So I think a lot of it comes down to matching it, and yet the heart of the issue becomes the engineer. That's where most of the problems occur, is lack of engineering experience and lack of engineering education on how to set it up, how to communicate, and how to adjust. Too many engineers are proud of their work, which they should be, but proud of the work means that you also have the ability to adapt and recognize what's right for the project is your answer, not what you predicted. You know, nobody's that good. And so recognize that, have your owner prepared, have your driller prepared, and understand when there's an honest increase or change in price, and be fair about it. So it comes down to engineering. And this is one of the biggest problems that I see in the industry. I have a very difficult time hiring people out of school or anywhere else. There's no training program. I shouldn't say no. There's very limited training programs even available. And the training programs don't include a lot of the hands-on, like the technical trade schools. We're finding a lot of our best students come out of trade schools where they have to go out in the field and actually work with the tooling, or universities that require outside field work with somebody during the summertime, internships. Things like that are invaluable. You know, if you go out, you're doing an interning as a student with a contractor or an engineering firm that is knowledgeable, you'll probably find you have a job waiting for you before you ever get out of school.
Oh.
That training is worth a lot, and not to mention it's just a real fun field to be into. There's no right and wrong answer. Everyone's got proper input. I don't care whether you're in school or you're the owner of the company. Everyone's got valuable input. Your job is to build the team, because you're the core of the knowledge as an engineer. Build the team, including the owner, all your engineering support, the contractor, anyone else that gets involved, like regulators, municipalities that you're using their land or you have permission to be on it. All these people are part of your team. They all have valid input. Your job as the engineer is bring them all together to get this project done, and your client is the project. Even though you might be signed up for somebody else, you're working to make the projects a success.
A great way to look at it. And, you know, more projects would be successful if everybody had that mindset. You know, it's a good way to think about it. I was going to ask, you know, what could be done to improve the quality of the industry, but I think that that mindset really does capture it, right? It's like if we're thinking about it as the project first, we're going to all do our part to make sure the project is successful.
That's correct. I sort of answered that one in part on the other one, even though I, in my previous discussion, but it's a real good point. What we can do to make things better, the best thing right now, there's a lack of people in the industry. Start training new students, get them excited in it. And I think the best way to get people excited and get their passion going, put them on a drill rig. Let them see what it can do. Put it back in a pasture somewhere where no one's going to get hurt, but let them feel that horsepower underneath, and then learn from the textbook, what am I really doing, and am I doing it successfully or not? Those people are in huge demand. That would help a lot of the issues in the field.
Awesome. Where would you say that? Yeah, no, there's a lot of opportunity. And where would you say that the industry improvements will come from? Like, where do you think they're going to come from as we look forward?
I think urbanization, as it always has been historically, is going to be at the heart of it. And then it's up to everybody else that lives, say, in an urban area or the environmentally sensitive people that say, we have to live on this earth and we got to have this earth available for our kids. Putting those together creates an opportunity. Then the innovation is going to come, I think, from the contractors and the tooling people more than anything else. Then it's up to everyone else to acknowledge it, take advantage of it, give the contractors a chance to use the technique and refine it, which may cost you a couple of bucks, but recognize down the road, you're going to get the benefit of that if you're an owner by not having the phone. We have one project, for instance, going underneath the river. Very simple project, except for the 5 towns converged in the middle of the river at one point. We had to go underneath that point. So in this case, we took the study as best we could, said we don't really know anything, not enough to make the towns happy. And there was noise, there was, live oyster beds, all these, everyone had issues. Plus we were in a residential neighborhood. We gave the contractor $25,000 for the crew, not the company, the crew, to split. And it was based on every time one of the mayors got a phone call, you lost part of that bonus. So they shut down, late afternoon when there was getting tests and kids were studying and needed the quiet. They went up and shut down when they were asked to. No questions asked. They kept 100%. So it broke up because that was my idea and it worked. And I didn't expect that. So it was quite gratifying. None of the mayors got a phone call. The crew doing the work got the money.
Wow, that's powerful. That's powerful.
Yep.
And it just goes to show that, thinking outside the box, it's more than the equations, thinking about the outside the box. And then, we're all people. We're all people on this planet trying to solve these challenges. And the reality is that, if you get to the hearts of the people, you can find a good solution. Wow. So before we take our break, I'd be curious, what's the final piece of advice you'd like to give to, especially the young engineers out there before we go on our break?
That's a good question. I thought about that and wrote down a couple of things. I just got to find out what I did with them. But as far as advice, think outside the box all the time, and you try to figure out that how you're going to communicate all these complex ideas to the various team members in language that they can understand. So we're technical people. Unfortunately, that has come to mean that we know all the big equations and the big words very well, but we don't have a clue how to communicate that meaningfully to other people. even going in and saying, all right, we have a glacial geology here consisting of alluvium and glacial till, you've lost it. Nobody, even contractors, won't have a clue what to expect out of that because they're big words. If you come in and say, all right, I got a bunch of really dense boulders, cobbles, big hard rocks, and it's going to be along the full length, except for at this little end where I got a bunch of sand piled up, but it's pretty dense. Contractor's going to understand that. You can explain that, and then what does it mean to the owner with regard to cost? You can explain that to the regulators and the property owners, because Mother Nature's just going to let you do certain amount of work and type of work with those conditions. So you can explain that to the regulators so you don't get stuck with bad regulatory conditions. So communication, I think, is the key element in understanding what you're doing to be able to communicate it to whoever's listening to you in their language.
Very good. Very good. Well, thank you so much. We're going to come back in just a minute and close this one out with Brian in our career factor safety in segment. Stick around.
Before we dive in, we'd like to recognize our sponsor for this episode, PPI, a leader in engineering exam prep for the FE and PE exams. PPI provides expert prep courses and study resources designed to help you pass the FE and PE exams the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. Check out PPI today at ppi2pass.com to see all the options available for FE and PE exam prep.
All right, welcome back. It's time for our career factor safety in segment. In geotechnical engineering, just like many disciplines of engineering, it's important to incorporate a factor of safety into your design. But what about incorporating a factor of safety into your career? Today, of course, we're speaking with Brian Dorwart, PE/PG. Brian, you've already had a very successful career. And when you look back on your career, what's one thing that you think you implemented in your career to give yourself, let's call it a factor of safety in your career?
That's a real good question. It comes down to what is factor of safety? And what that is a statement based on your knowledge and your work. How good do you feel about the answer? If you don't feel real good, you have a high factor of safety because there's a lot of unknowns. If you feel real good about it, you may cut the factor of safety down. But you got to stay within industry standards so you're measuring yourself against other people doing the same thing in the industry. So that's actually what factor of safety is. And with that comes the knowledge you have inside. How good do you feel about what you've learned? How good do you feel about how you were prepared? And a lot of this starts in school. I had a great opportunity of working with Professor Seelig, who is very good in his field, but I worked as a research associate with him. He says, you don't know anything until you go out and try doing it in the field. And so I got shoved out on facilities like the fast track facility out in Pueblo for months, putting in instruments, then watching a freight train go over those instruments until after several million miles, the train would break. Then we go out, put our instruments in again. So we get to watch things break. Well, in doing that, they had other facilities. We had high-speed locomotives that we were working with. The track was only 7 miles long for that facility. So we were forced to watch as they put 2 JP4 jet engines on the back of the locomotive to make it go fast enough. It did. It went off the end of the track. We found another couple miles down the road, buried in the sand. So experience in the field can be fun, but it also, you need to learn. Everything in the field that you're going to learn about is how is it going to break? And so that's what Professor Seelig taught me, is how is it going to break? Look for how it's going to break and work around it, because that's where your gut feeling for your factor of safety comes from. So he's the one who taught it to me, and I've followed that ever since, of The more experience I get, the more I'm willing to bring the factor of safety down, but only to a limited extent, because in geotechnical engineering, it's a humbling sport, so to speak. You're never going to know enough to be certain about it. And you want to make sure you're certain enough that no one's going to get hurt, or you're going to have a bad catastrophe. So again, factor of safety, how good do you feel about your knowledge? That comes from pretty much my first engineering job at GZAD through my last one at Brierley Associates now. Is I've always had somebody that said, all right, you sort of like what I like. Let's work together on it. And he acts as your mentor. So learning about factor of safety and then having enough guidance so you're not the only one. There's other people that'll help. Those two things I find are the most influential is my mentors and my first instigator, Dr. Seelig, and showing everything's going to break. Your job is to figure out how it's going to break and make it not happen.
Oh, that's a really cool way to think about it. Brian, thank you so much for coming on. Thank you for sharing all the great insights with us and the listeners. And I'm sure that this information is going to be helpful for our listeners. And if listeners want to reach out, what's the best way for them to find you?
Oh, they can reach me online is probably the best way. My email address is BDORWART@BRIERLEY Associates.com, or you can go to our website at www.brierleyassociates.com. We're a very small company. They'll find me, not a problem. So please feel free to reach out. I do work 7 days a week. Reach out anytime.
Excellent. Well, thank you so much for coming on the show. This was great.
Thank you very much for this opportunity. I appreciate it.
Awesome. I hope you enjoyed the episode today. We would love to hear your feedback, comments, and/or questions. Please feel free to go to geotechnicalengineeringpodcast.com, where you'll find a summary of the key points discussed in today's episode, that being episode 46, as well as links to any of the resources, websites, or books mentioned during this episode. Until next time, we wish you the very best in all your geotechnical engineering endeavors. Peace.